Assalamu alaikum everyone. Today we are going to start chapter 9, design via the root locus. So basically the knowledge that we have gathered from previous chapter 8, that we have to use to graphically solve the problems that we face in our control system. One of the problems is steady state error. We don't reach the destination that we look for. The other problem is the transient behavior. So the percentage overshoot, or the settling time, rise time, or the peak time we want according to our desired specification. So all these things can be actually improved with the help of the root locus technique that we have seen in the last chapter. So the topics that we are going to see here is actually summarized in these 5 points. Improving the steady state error. So this is one, using the root locus. Basically, the first three is in cascade form. Okay, so only the fourth one is actually in terms in feedback form. So don't worry, I will draw the block diagram to show what is meant by feedback and what is cascade. And then we have whatever the compensator or the controller that we are going to design to have our desired transient behavior, as well as required amount of steady state error. So that thing we have to realize. Realize means actually physically we have to implement using maybe op-amp, amplifier, and resistive and capacitive components. So this is what it's called a realization. This is the last topic of this chapter. So this is what we are going to see in this chapter. Let's start with the basic idea, how actually we are going to improve this system behavior. So first of all, say that what we know so far from the root locus. So start from there, that will be easier to see. So say that we want to, we have a particular root locus, something like this. Okay, so we have a pole here, open loop pole somewhere here, another open loop pole here, then we have another pole here. So for a system like this, what we know is we are going to say what should be the type of our kg of s, h of s. So as it suggests that it will have something like this. K may be variable, then we have our s plus say 1, s plus 2, and s plus maybe 5 or something like that. Okay, so this is how it looks like. And from the previous knowledge of root locus, we know that we will have the root locus segment will be this one. So this will be one segment, and the other segment will be this one. Okay, so these are the two segments. And from the chapter 8, we also know that we'll have, since we have three finite root, we'll have three finite, infinite zeros will be also there. And the direction will be, so far as we have seen, is actually 60 degree, 180 degrees, and 300 degrees. Okay, so basically what we are going to see is, we are going to see if we find out the breakaway point, we are going to see we'll have a curve like this, something like this. And the other one will be identical and going downwards, something like this. Okay, and this one is going in that direction. Now, suppose that they are saying that we have to follow a percentage overshoot of our response. So arbitrarily 20% or 60%, whatever it is. So we solved with 20% last class, so that is why we know that it will give you a zeta value corresponds to 0.4559. and a theta angle corresponds to 62.877, something like this. Okay, so we actually have to draw a 63 degrees line somewhere like this. So then we'll find a point here. Okay, so this point is actually is on the root locus, and that will give you the corresponding values of uh, percentage overshoot fulfilled. No, but say the whole line here is actually giving the same percentage overshoot. So say we want to speed up our system response. So how can we speed up our system response? So this point correspond here is omega d, and this point correspond here is sigma d. Okay, so to speed up the response, we want to reduce our settling time. So settling time, chapter 4, is 4 by sigma d. So that means the value of the sigma has to be increased. Then your settling time will be reduced. So that means we are speeding up our response. Similarly, say peak time we want to reduce. So for that, the formula is pi by omega d. So omega d is increased. That means your peak time will be also increased. So we are achieving the peak value higher. We are achieving the settling times peak value, peak time smaller, as well as the settling time smaller. That means with the speed of the transient response will be faster. So basically, what we are interested is, we are not interested about this point. So this point is A. So we are interested about on the same line at this point, say point B. So the question is it possible with the current root locus that we have to go from point A to point B? So what do we actually want? We want point B to be on the root locus. So how can we achieve that? This is what we are going to see in this chapter. Okay, so definitely the system that has a root like this will never actually go through point B. So it will always go through point A, but it will not go through point B. So how can we actually take our root locus to from point A to point B? This is what we are going to see in this chapter. Okay, so what are the ways? The first and the easiest solution is replace the existing system with a system actually whose root locus goes to that point. Okay, so this is one easy way to do that. Okay, but this is expensive solution, though the solution is simple, uh, that replace the system entirely and bring a system whose route will be actually the root locus will be going through that particular point P. But this is expensive. Like we have our maybe our generator in the IoT substation. So the price of that generator is over 10 billion, 10 million. Okay, so expensive device like that cannot be actually replaced that easily. So that is why we have to do something so that with keeping our system intact. Okay, so how can we move from point A to point B? This is what we have to try to find out a solution like that. Okay, say that our original plant is something like this. Okay, so plant, and we have a say original gain, only a pure gain, say K, or original control, or whatever you say that we have. But with the value of this gain K, it is not possible to bring the system to point B. So what we are going to do? We are going to introduce another one here. Okay, so we are going to introduce what you call compensator or controller. Okay, so say this is your GCS. Okay, so we call GCS as, sometimes we call it compensator, or also we call it controller at times. Okay, so basically we have to bring some dynamic transfer function GCS that will actually force our root locus to go from point A to point B here, somewhere here. Okay, so how can we do that? Now, this compensator, let us discuss a bit more about the compensator. The compensator can be implemented using active components, okay, like amplifiers. So it can be using active components. So once we are using active components, sorry, it should be actually going. Okay, so we can use active components and then actually call it controller. So it should go there, active components, like amplifier. And the problem is amplifier doesn't run without the power supply. So you need also a power source or power supply. Okay, so this is that disadvantage. Okay, so active component with the help of amplifier, as well as and for compensator, we need passive components, passive components that is using resistor and capacitor. Okay, so either use active or passive. The active one gives you ideal compensation. Okay, so this gives you ideal compensation. And this gives you can say non-ideal compensation. Non-ideal, that is actually non-ideal compensation is actually known as compensator, and the ideal compensation is actually known as controller, non-ideal. Okay, compensation. Okay, so this is the two way to implement those. And the third thing that we are going to discuss is actually why we need these compensations. Now, first of all, is basically uh, if we introduce this, then we can actually have more flexibility. What is the flexibility? Anywhere in the root locus, we can choose any point and say here we want our system to be, or here we want our system to be. So any point we can choose, and then we can design our compensator in such a way that our root locus eventually goes through those points. So this is the advantage. Any single point you can choose, and accordingly you can design your compensator to have those desired characteristics. Okay, so now the point is there is two type of compensator, as we already said. One is your uh, the active type of compensators implemented with active components, and the other one is implemented with passive components. And then now, how can we actually improve the transient behaviors? Just like that, we said that we want to make our response faster, so system response faster. So how can we do that? So for doing that, actually, we can introduce differentiator. So so instead of just forwarding the arrow term with the proportional gain, we also, this is your maybe proportional, then we will also forward it with a differentiator. Okay, so at the very beginning, so your output of the plant is 0. So we have something like this. So two results. So this is your differentiator. So differentiator can be ideal, can be non-ideal. If it is ideal, then it is called controller, and if it is non-ideal, then it is called compensator. So with the differentiator involved here, at the very beginning, say this is your plant, and your output is 0 at the very beginning. Okay, so you just started the system. So you have given the input, say 220 volts, something like that, and your output is 0. So now you have a very large error value here. Okay, so error value 220, whole value is coming here. So there is a high transition from 0 to 220 volt. So differentiator only works in the transition. Whenever the value is steady, the differentiator will give 0 output here. So it will have no contribution. So whenever there is a rate of change only involved, so at the very beginning, so this there will be a high rate of change, and because of that, the differentiator will make the value even bigger by differentiating it. So with a very large magnitude of driving signal, the plant will be driven, and as because of that, your system response will be faster. It will approach to the destination quicker. Okay, so that is why to improve the transient behavior, we actually introduce a differentiator. So if it is ideal differentiator, then we call this one as a PD controller. So ideal differentiator is known as PD controller. So proportional and derivative controller. Okay, so ideal one is known as proportional derivative controller. Okay. Now, if it is ideal, okay, what does it means? Ideal? Ideal means it has to be implemented by active components. Okay, so like amplifier with power supply. Now, if it is non-ideal, then what do we call it? We call it lead compensator. Non-ideal, then we call it lead compensator. Why lead compensator? That one will be discussed in chapter 11. So whenever we'll see the frequency response, then we are going to see that it actually advances the phasor. So that is why it is called lead compensator. Okay. So and that has to be implemented by passive networks, passive net components. Okay. So these are the two terms, and these are the two technique to improve the transient behavior. PD is proportional derivative controller or lead compensator. And then if you want to improve the steady state error, then from the chapter 7, improving steady state error. So from the chapter 7, what we have seen is that if a particular system if we increase the type of the system type is increased, then the steady state error is actually improved. So increasing the type of the system means we're introducing pole at the origin. So 1 by S. 1 by S is nothing but an integrator. So if you have actually increased the system completely with the active networks, so active components, then it is possible to have a pole at the origin. origin. So if it is possible, and this is what is called ideal an integrator, or sometimes it is also known as ideal compensator. So ideal compensator. Okay. So ideal compensator, similarly like that you have seen in case of the transient behavior improvement, we call it ED controller. Here we call it PI controller. Okay, so P is same as before, proportional, and I is integral. Okay, so integral controller. Okay, so PI controller. And if it is consists of passive components, then we have to we call it. Then the problem is pole at the origin is not possible. Okay, so pole very close to origin, Okay, but at the origin it is not possible because of the capacitor and the resistor. It is difficult to implement a ideal integrator. So this is actually non-ideal integrator, and that is why it is also known as lag compensator. Okay. So the lag compensator somehow will improve the steady state error, but it will not be able to eliminate the steady state error. So introducing a zero at the origin actually brings your steady state error to zero, where it will reduce by some margin, but steady state error will never go to zero value. Okay, so this is the two factors. So basically, if you can afford the active components and the power supply with the system, then it is better always to go for active networks, that is PI or PD controller, or you are going to see as well that whenever we are implementing together, then we call it PID controller. So the system's transient as well as your steady state behavior, both will be improved. Okay, so then we call it uh, PID controller. So there is, I think, Article 9.4 somewhere there. But let us today just see that how to improve the steady state error part. That means Article. Okay, so before going into that, there is two configuration for having this controller. So two configuration. The configuration one is called two techniques basically. So compensation techniques. There is two compensation techniques. Compensation techniques. At the introduction, we tried to say that. So one of them is cascade. And the other one is feedback. Okay, so in the cascade, the block diagram representation of the cascade is something like this. Say this is your okay, so we have in the compensation is actually in cascade with your original controller and the plant. Say this is your G1S, next one is G2S, next one is G3S. Okay, so this is your plant. This is your original, only the gain controller maybe, or original controller. Okay, and then we are introducing the new one, which is a dynamic one. So dynamic, we are saying that it contains S parameters. That is why you're calling. Okay, so RS. Okay, so this is what is known as your cascade compensator. Cascade compensator. Okay, so in cascade with the original and the controller and the plan. So the second one is the compensator is in the feedback path. So basically, you will have your original controller as well as the plant as it is. Okay, then in the feedback path, we have our compensator. So this is yes. This is G2S maybe. G2S is your plant. This is your G1S, the original controller. Okay. And this one is say HS. So this one we call feedback compensator. Okay, so this is the difference. One technique involves cascade or in feed forward path, and the other one is in the feedback path. This is the only difference. And now, the earlier topics in this chapter, we are going to see the cascade form because this is easier to deal with. Then later on, we will also see how to do the same thing with the feedback. Okay, so let us start with our cascade designing. So Article 9.2. So whatever we have discussed so far is actually Article 9.1 we covered. So now Article 9.2 is improving steady state error via cascade compensation. So improving steady state error via cascade compensation. Okay, so we already discussed what to do. So there is two techniques. One is called ideal compensation, ideal integral compensation. Okay, so or the other one is called lag compensation. So two methods. So basically ideal integral compensation. So we also call this one as PI controller. Okay, so the other one is we call it lag compensator. Okay, so non-ideal or lag compensator. Lag compensator. Okay. So I'm just repeating the things more than once because then it will be easier for you to recall. So this one is expensive because you need power supply and active amplifier. So this is expensive, and the other one is non-expensive, but expensive, but it gives you zero steady state error. So it is expensive, but zero steady state error is not possible. So you actually have to decide which one you should go for. Okay, so if the steady state error is very important to you, to make it zero, then we have to go for expensive PI controller. Otherwise, we may be happy with the lag compensator. Okay, so let's start with the first one, that is ideal integral controller. So first one, ideal integral compensation, that is say we have a block diagram, something like this, without the compensation. Let's discuss that one first. So we are starting with the first method. So in the first method, we have, say, K here. Then we have G of S here. Okay, so this is CS and this is your RS. Okay, so now look at here. Say arbitrarily, just like the previous example, arbitrarily what we have is, let's say, with 3 poles, just like the previous case. So we say we have something like this. Okay, so say one pole we have here, one pole we have here, and the other pole we have here. So what will be the shape of the root locus? So basically, one of them will be going in that direction. Okay, so other two will be merging together to find out a point, breakaway point. So from that breakaway point, vertically they will come, and one of them will be going in that direction, the other will be going in that direction. Okay, so now what we are trying to do is to reduce the steady state error. Say at any particular point we are here. So now our system goes through this particular point A, and we want to we are interested about reducing the error. And from the system transfer function that we can see that K, G of S, H of S is actually having something like this, 1 by K maybe S plus S plus A, S plus B, S plus C. Okay, so this is what we have. So this is minus A, minus B, minus C. So to have what will be the error for this particular case? So we know that G of H of S is 1. So basically we can say that our steady state error for this particular system is, the system type is basically we have type 0 system. So there is no S term here. So S to the power 0. So we have to apply a step signal. So if you apply the step signal, the formula is you have to actually calculate Kp. So Kp is limit S tends to 0 G of S. In this case, K G of S, H of S is the same thing. So basically what we are going to find is we have to put the value here, and it will give you K by A into B into C. Okay, so then we have finite value of Kp, and also steady state error value will be also finite. So 1 by 1 plus K, A, B, C. So basically we'll have some finite result here. So but what we want to have, we want to actually have zero steady state error. So what is the possibility of having the zero steady state error? We have to increase the system type. So actually we have to introduce an ideal integral compensation. We have to introduce a pole at the origin. So let's see what are the problem that is going to happen. So we are actually willing to have zero steady state error, and because of that actually we are introducing a pole here. So pole at the origin, it can actually bring zero steady state error. So is it actually happening with an isolated pole at the origin or not? Let us look at that one. So what we have is something like this. Let us draw the axis first. So approximately this is what we had previously. So but we have pole here, we had a pole here, and we had a pole here. So now we have introduced and also from the pole, the formula that we know, the pole angles, zero angles minus pole angles has to be 180 degrees. So if you draw the lines from these poles, then what you are going to see is that this summation of these all angles actually has to be 180 degrees. Now if we introduce another pole at the origin to make the steady state zero, so what we are going to see that now our root locus has been changed. So now this portion is in between the root locus, and this portion is in between the root locus, and this segment is no longer on the root locus. Similarly, this segment. So basically, the shape of the root locus is changed. Also, the angle is also changed. So angle will be now twice k plus 1. 4 of the pole. You have 4 by pi by 4. So pi by 4 means actually 45 degree, 135. So basically, you will have something like this. Guiding lines will have some guiding line in between this. So basically, these two will be merging together. Then one will be going through that one, the other will be going through that one. Similarly, the one will be going through that one, and the other will be going through that one. So for what we have seen is our root locus itself is changed. So we are no longer going through the point A. Because of the introduction of this particular pole, now the contribution of all the pole angles is actually no longer 180 degrees. So theta is no longer 180 degrees. So that is why point is no longer on the root locus. Okay, so it is no longer on the root locus. So this is the problem that we are going to see. So that is why it is actually not possible to introduce a single pole at the origin and to keep our root locus, previous root locus intact. So that is why what we have to do is we have to introduce a pole as well as we have to introduce a nearby zero. So a nearby zero eventually will nullify the effect of that particular pole. So what we are actually trying to say is this. So what we are trying to say is that for ideal PI compensation, what we are doing here is we have a original systems pole somewhere here, and we are introducing a pole here, as well as we are introducing a very nearby zero. So now if your point A was somewhere here, so your point was somewhere here. So now the contribution of all the angles, if we draw from that particular point somewhere here, because if you draw the points, as you can see here, the contribution of this pole and zero is actually cancelling each other. So their contribution is cancelled, because we know that the summation of all zero angles minus summation of all pole angles has to be equal to odd multiple of 180 degrees. Is it okay? So now this pole zero contribution, angle contribution is cancelling each other. So more or less this previously used these three angles is still contributing to 180 degree, and that is why maybe the point will be slightly changed, very slightly, but will be very close to the original point, maybe somewhere here or somewhere here, slightly changed. Okay, but more or less we can say that that particular point, the behavior very close to that point A is will be also very close to the transient behavior of that system. So without changing the behavior of the system, this is how we introduce one pole at the origin to make the steady state error zero. And then we introduce a zero very close to the pole so that the angle contribution of the pole and the zero is nullifying each other. And we are following a curve root locus plot very close to the original one that we started with. Okay, so this is how you have to reduce the steady state error to zero. Now look at your example 8.1, sorry, 9.1. Example 9.1. So example 9.1 is, so first one without first block diagram that has been given is without the compensation. So basically only the magnitude gain is K. And then we have a system, the one that we already discussed, similar to that, that is 1 by s plus 1, s plus 2, and s plus 10. Okay. So this is without the compensation, the system something look like this. And now let us analyze this system first. Then we'll go with uh, the compensation. So this open loop kg of s h of s here is actually kg of s h of s is k by s plus 1, s plus 2, s plus 10. Okay, so this is what we have. Kg of s h of s will be k divided by s plus 1, s plus 2, and s plus 10. So now look at number of the branches will be 3, and 3 finite pole we have. So number of the infinite line, because we already know from this previous chapter. So I'm just writing very quickly. That will be also 3. And your sigma A guiding lines will be summation of the pole minus summation of the 0 divided by pole minus 0. So basically minus 1, minus 2, minus 10 divided by, we only have 3 poles, so something like this. And that will give you minus 4.33. And theta A will be same as before. We don't have to calculate it. One will be 60 degree, one will be 180 degree, and the other one will be 300 degree, just as before. Okay, so similarly, we can also go for your j omega axis crossing. So j omega axis crossing will be calculated based on your, just multiply these 3. Okay. So if you multiply these 3, then what you're going to get is SQ plus 13s square plus 32s plus 20. Okay, so that divided by K. Now we need TS. So TS will be K G of S, H of S. In our case, it doesn't make any difference because H of S is 1, so we can just cancel it from there. So from 1 plus K G of S, H of S. Okay, so now if you put the value, so we don't want about anything about the numerator, so we only want to know about the denominator. Denominator will be simply with whatever the parameter that we have calculated. With that, in addition, we'll have K will be added with that one. So 20 plus K. So 20, let me erase it. So okay, so 20 plus K. So basically s cube, s square, s to the power 1, s to the power 0. Okay, then we have 1, 13, 32, 20 plus k. That is why actually we have gone through the chapter 8 in detail, because of the fact that we have to apply those in this chapter as well. So this time we'll be trying to do the thing a bit faster. So what we are going to see that if you multiply 13 into 32, then you have minus 20 plus minus k divided by 13, then what you are going to get is 396 minus k divided by 13. And this one simply will be coming here, so 20 plus k. So as we know, this is our only chance, because in the rest of the cases it is not possible to make 0, and the last one is only the coefficient, so it will not also be helpful. So what you can say that value of the k will be 396, and corresponding value of j omega axis crossing will be s square into s square into 13 s square plus 20 plus k equal to 0. So 13 s square 20 plus k is nothing but 416. So you are going to get s equal to plus minus j 5.657. 5.657. We have already seen all of this, okay, in the last chapter. So that is why we have to go very quickly. And even though in the problem they will ask you only to design for particular steady state error or particular transient behavior, but inherently actually you have to plot it first, then you can go for. So these are the things must do step before proceeding to figure out what is happening with the designing. Okay, so this is the j omega axis crossing that we figured out. Next thing is the breakaway breaking point. Even though it is not that important, but for refining the sketch, you can actually go for that one. So summation of the poles 1 by sigma plus pi should be equal to summation of 1 by sigma plus ji. So in our case, we don't have j, we only have pi. So basically 1 by sigma plus 1 plus 1 by sigma plus 2 plus 1 by sigma plus 10 equal to 0. So now if you just do a bit of calculation, then what you are going to see is final value will be 3 sigma square. Okay, so 3 sigma square plus 26 sigma plus 32 equal to 0. Now from that one you can find out two values of sigma 1, 2, that is one is minus 1.485, the other one is minus 7.181. Okay, so but as you can see from our out of these two, we're going to see that this will be appropriate. This will not be appropriate because our root locus exists in between this point. So only the appropriate one will be actually minus 1.485. Okay, so let us try to plot it. So now let us draw the diagram first. Okay, so okay, so at 1 we have 1, at 2 we have 1, and then we have at 10. So somewhere here. Okay, so we already calculated 1.485. So somewhere here is your breakaway point. Definitely, we know that our root locus is going to go through somewhere this. as well as in between these two. They're merging at 1.4 minus 1.485 point, and we have 1, 2, 3, 4, 5 point something. Approximately here is your crossing point. Okay. Okay, so vertically they will come here 1, 2, 3, 4, 5. So here somewhere here as well. Okay, so our curve will be somewhere like this. It will be going straight, maybe then eventually we will go through that point, and finally then minus 4 point. Let me give the points that will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so minus 4.33 somewhere here, then you should have a 60-degree line. Okay, so then you should have a 60-degree line. Okay, so somewhere around there. Okay, so sorry about the drawing. Drawing should have been from slightly downwards. It should be started. Okay, so this is something that we are going to get. So eventually, maybe it will start somewhere like this. Then going through that point, eventually it will go somewhere like this. So it will approach to that asymptotic lines. Similar thing will be going downwards. Now, the example problem that we are saying is that we actually have to maintain a particular zeta value. So zeta value is given 0.174. So we actually have to figure out which point corresponds to this one. So for this particular value of zeta, that we can see that cos theta is basically cos theta equal to zeta, and that theta is basically cos inverse zeta. Okay, so cos inverse 0.174. So cos inverse 0.174 is basically it is becoming angle 79 point. Okay, so 79.9795. But actually you have to draw the angle from real axis, so it has to be 180 degree minus theta. So basically 180 degree minus 79.9795. So eventually it will be 100.02. Okay, so a point that we have to figure out is at angle approximately 100. So with a 100-degree angle, we can draw a line like this. We can draw a line like this. Okay, so this gives us the point intersection, the point in the root locus that will eventually give you the value of the percentage overshoot that we're looking for from this particular value of zeta. So this particular value, to us, it approximately seems like something very close to 0.7, minus 0.7, and then 1, 2, 3, 4, plus 4, something like that, plus 4.23, something like that. Okay. But we are not taking the value that is coming from the graph. In your case, you actually have to take whatever the plot that you are getting. But I am taking the book's value because of the fact that then you can verify the book's value. Okay, so according to the book's value, the intersection point is somewhere at minus 0.694, that is very close to 0.7 our estimation, but our vertical line wasn't that good, so that is why the vertical value couldn't match. So the vertical value is 3.926. Okay, so but shape is similar, but somehow our value wasn't that good because of the tab that we are plotting here is not that precise, and also my drawing is maybe not that good. So, but in the exam, whatever value it comes for you, you have to take that corresponding value. This time I would have been taking that one as well, but I already have verified the calculation of the book, so that is why I'm just taking the same value as before. Okay, so now once we know the point, we can easily find out the value of the gain for which actually that point is on the root locus. So what will be the value of the gain k? So the gain k is product of the pole lengths divided by the product of the zero lengths. Okay, so product of the pole lengths divided by the product of the zero lengths. So what is the and do you have any zero? No. So basically, our case is very, very simple. So we only have the product of the pole lengths. Okay, so product of the pole lengths. So how to find out the pole lengths? So basically, as you can, if we know the point, so we'll have a vertical point, vertical distance, we'll have a horizontal distance. So Pythagoras from each point will give you the corresponding length. So say we want to write it from this one. So Pythagoras for this one will be basically root over 10 minus 0.694 whole square plus the vertical length is always same, so 3.926 whole square. Okay, so this is the pole length from the pole at minus 10. So this will be multiplied with the next pole length. So next pole length is at 2. We have the next pole at 2. So basically 2 minus 0.694 whole square plus 3.926 whole square. So I multiplied with 1 minus 0.694 whole square plus 3.926 whole square. So if you multiply these three, then you are going to get approximately 164.588. So this is how you have to calculate the gain at that particular point. Okay, so now we know that we have three system pole, isn't it? So one pole is at here, somewhere here. Okay, so this is what you know, that one pole will be here, and the gain for which it is happening is k equal to 164.588. So whatever the other two poles, so another pole will be definitely here, which will be a complex conjugate. So we are not interested about this one. We can easily verify that. And what about the other one? So other one will k equal to 0. It was here, isn't it? At k equal to 0. So where it will, what will be the location of this higher order pole? So these two we are calling that dominant second order pole. So these two are dominant second order pole. Okay, so this is higher order pole. So, and also we actually have to verify that whether our approximation is correct or not, because of the fact that we have said in the last class that the approximation says that the real axis value has to be at least 5 times. Okay, so if this higher order pole is at least 5 times away from the dominant second order poles, then we can say that our system approximation or the approximation of the calculations are correct. In our case, actually, we don't have to do any calculation because we know the real axis segment of this one is 0.694. Okay, it has to be above 10, so it is almost more than 10 times. So we don't bother about it. But still, if you want to, if you're interested about the location of your higher order pole, how to calculate that. So uh, we actually have to search for the point. We have to search for the point that will give you, because that at that point also your gain value K has to be 164.588 or closer to that. So where that higher order pole should be. Okay, so let's do that calculation of K. K is the same formula because in our case now only the pole lengths, product of the pole lengths. Okay, so product of the pole lengths, and product of the pole lengths here is, as you can see, all the open loop pole are at real axis, and our higher order pole will also be on the real axis. So you can say that say higher order pole at -11. Okay, so at -11. So since we're just taking considering the magnitude, so 11 minus 10, the distance from this pole 10 at -10. So into 11 minus 2 from the next one into 11 minus 1. So basically what you're going to get is 1 into 9 into 10. So basically 90. So this point is equal to -11 cannot be on the root locus for value of gain K equal to 164.588. So let us apply the next point. So you have to do a bit of either you have to apply the MATLAB formula, MATLAB program to figure out where the pole location should be, searching the pole. That will give the corresponding gain of 164.588. Or what you can do is you can do a bit of approximation like this. So say next point is S equal to -11.5. So if it is -11.5, then what you have is 11.5 minus 10. Then have 11.5 minus 2. Then you have 11.5 minus 1. So what you are going to get here is 1.5 into you have 9.5 into 10.5. So now if you multiply the three value, then what you are going to get is approximately 149.625. Okay, so still it is not 164. So, but we are in the right direction because of the fact that the magnitude actually increased. Okay, so we also know that magnitude is going to increase because at -10 K equal to 0. So you are going towards the infinity is actually increasing the value of the magnitude. So say K equal to, say S equal to minus 11.6. Okay, so if it is the case, then you have multiplication with 1.6 into 9.6 into 10.6. And this gives you approximately 162.816. Very close, but yet not the value that we are looking for. So -11.61. Okay. So then what you are going to get is K equal to 1.61 into 9.61 into 10.61, and it is almost there, 164.158. So maybe the point will be 11.6105, something like this. So, but it is good enough as long as our approximation says that we can say that 11.61 is the higher location of your higher order pole. So basically, you can say that somewhere 11.61, somewhere here. You'll have the higher order pole for the magnitude of k equal to 164.58. So this is how you have to find out the higher order pole as well. And then you have to approximate, apply the approximation that whether it is 5 times away from our the dominant second order pole or not. Okay, so far what we have done is actually we have just done the analysis for uncompensated system. Just plot the root locus, figure out the point, and now let us calculate the steady state error for uncompensated system. So now k g of s, h of s of uncompensated system is k g of s or h of s of uncompensated system is, we already know the value of the k, isn't it? K is 164.588. Then you have s plus 1, s plus 2, s plus 10. So we are actually, I'm not sure whether you recall or not. So we started with the scenario that our state, we are actually trying to reduce the steady state value. So for steady state value, we have to find out, in this case, the system is of type 0. So basically Kp we have to calculate. So Kp is limit s tends to 0 g of s. Say that whole thing can be g of s because h of s is 1. So k g of s is your forward path transfer function. So what you are going to get here is 164.588 divided by 2 into 10. So approximately we are going to get is 8.229. Okay, so steady state error is 1 by 1 plus Kp. So basically 1 by 1 plus 8.229, and that will give you approximately 0.108. Okay, so all these things, whatever we have done up to now, is for uncompensated system. Now they are asking us to examine our system behavior, system response for a compensated system like this. K s plus 0.1 divided by s is our compensator. Then we have our original plant as it is. So that is 1 by s plus 1, s plus 2, and s plus 10. So what we are interested about, the steady state error, because we know that angle contribution from this pole and 0 will be very close to each other.